Okay. Hello and welcome to our presentation on the network topology loop problem. I'm Tina Puzzo.
I'm Alan Garcia.
I'm Meixuan Chen.
And I'm Christopher Schelb.
All right. So over the next few slides, we'll be exploring the network looping problem. This issue occurs when a network has an information stuck looping, i.e., it's sending and receiving the same data repeatedly. The solution for the looping issue is based in minimum spanning tree network protocols. These protocols will inevitably be utilizing MST algorithms, of which we will also be covering. Over the next few slides, we will see the protocols, their pros and cons, their history, as well as the future of solutions such as theoretical minimum spanning tree algorithms. A little background on our presentation. In this presentation, we will be showcasing our exploration into historical development of spanning tree-based network protocols, as well as theoretical minimum spanning tree algorithms. We will be looking at layer 2, the data link layer. This layer routes traffic between devices on a physical link, usually on local area traffic. So what is the problem we'll be looking into? One of the major features of data link layer network topologies is the presence of broadcast packets used to transmit data. The translating of data from one place to another, like one switch to another switch, can have its issues. The big three issues are broadcast storms, unstable MAC address tables, duplicate frames. So what do all these issues have in common? They're all data link layer topology loops. All right, so we're going to be looking at broadcast storm. This is caused by a layer 2 topological loop. This is a looping issue that can take down an entire network. The only way to fix a storm when it occurs is to physically disconnect or reload the switch. Otherwise, the issue will grow until ultimately one of the switches breaks or fails. This is why it's so important to put in place protocols that ensure this kind of thing won't happen, such as the Minimum Spanning Tree Protocol, or STP, that we'll be covering in the next few slides. All right, so what is STP? The Minimum Spanning Tree Protocol is a protocol used in order to prevent loops when using redundant switches. There are different types of STP, but for the next few slides, we'll be looking at standard STP, or the original version of the protocol. Here we have a short overview of the protocol, which is elect a root bridge, place root ports into forwarding state, have each non-root switch select a root port, all remaining links choose a designated port, and then all other ports are put into blocking states. All right, so there's a lot of terminology that goes with this that we'll be going over. More STP terminology are ports and their states. The blocking state is a port that is blocking any traffic. Listening state is when the port is listening, therefore not learning or sending anything. The learning state is not sending any traffic, but is receiving and learning MAC addresses. The forwarding state is sending and receiving traffic, and then the disabled state is a port that is shut down. The Spanning Tree Protocol standard. The way this works is each switch will elect a root bridge using the root cost and local bridge ID. Then the switch with the lowest overall bid will become the root. All switches will initially believe that they should be the root. However, once they all share their BPDUs, the other switches will realize the best bid and change their root bridge as the correct one. All ports on the root bridge will enter forwarding state, and all non-root switches will choose the best path to the root ports, aka find the designated ports. Once the root bridge and designated ports have been found using lowest cost, all non-root/non-designated ports will be placed into blocking state. So, what's the need for improvement? The big issue with STP standard is convergence. Convergence as in the time it takes to do all the work to the point of stability. This is the biggest pitfall of standard STP. STP's protocol's convergence time is not optimal. Originally, an STP port had to wait 50 seconds before moving from a blocking to a forwarding state. Nowadays, network recovery is expected to be immediately. So, RSTP to the rescue. Like STP, RSTP has a lot of terminology that goes along with it. The Rapid Spanning Tree Protocol, RSTP. RSTP fixes the convergence issue by changing the consensus mechanism to allow ports to move into forwarding state faster. Instead of waiting for BPDUs from the root bridge to determine topology changes, each individual switch can sync with its neighbors, meaning each can independently navigate with its neighbors. The process can be repeated at each per hop layer away from the root until the entire topology has synced. Note how this propagation of network state is like the way a breadth-first search traversal moves through a graph. Syncing mechanism for RSTP. The syncing mechanism for RSTP allows the topology to automatically adjust all the port roles to correctly reflect which ports have the shortest path to the designated root bridge. All the ports which could not create a topology loop on the switch are immediately set to the forwarding state without a delay. This process is repeated for every non-edge port on the second switch. Since there can only be one root bridge per topology, the subsequent elections determine which switch has the shortest path to the root bridge. If one of the downstream switches has a lower bridge ID than one advertised in the BPDUs of the root bridge, the root bridge can change and the network can resync itself. In many cases, network administrators will initially set the priority of the desired root bridge to the lowest possible value to deterministically create the network topology. Here we have the pseudocode for RSTP.
So, minimum spanning tree. As you may have already noticed, the STP and RSTP both utilize the idea of minimum spanning trees. Understanding them is the basis of understanding how these protocols operate, why they work, and why they need improvement. Over the next few slides, we'll go over some algorithms used to find minimum spanning tree. Borowka's algorithm, the granddaddy of algorithms developed to solve the minimum spanning tree problem. Published by Czech mathematician Otakar Borowka back in 1926. The idea behind this algorithm is to build subtrees and choose the best edge for each vertex in the graph. Once an edge is picked, it will unite two components, creating multiple forests each iteration. The act of reducing the size of the graph by a factor of 2 is often called the Borowka step. This cut property is applied to reduce the number of subtrees and form the final minimum spanning tree. Our time complexity is of E log B. Prim's and Kruskal's algorithm, we have seen them in class, but we'll go over them again. Prim's greedy algorithm was designed by the mathematician Wojtek Jernik in 1957. A simpler version of Borowka's, it involves simply traversing the entire graph vertex by vertex and picking the minor edges iteratively. Time complexity in an adjacency matrix is O of B to the second power. The heap implementation is O to the E log B. Another greedy strategy published by Joseph Kruskal in 1956 is Kruskal's algorithm. The idea of this one is to pick the most minor edge, checking if it doesn't belong to the set of vertices that belong to our current tree. Time complexity on the standard implementations is big O of E log B, and with a binomial heap implementation which merges two heaps together, it's E log of B. And the main issue in minimum spanning tree generation can be solved by choosing a tree and verifying that it is indeed the minimum spanning tree. Based on this idea, many other algorithms emerged through bit manipulation and comparison. These algorithms were faster, though they were mostly used for scientific application and are common in software development scenarios. A restricted random access model was not found before 1990s when the David R. Karger, Philip N. Klein, and Robert E. Tarnian presented a randomized linear time algorithm approach to solve the minimum spanning tree in linear time.
Bernard-Child's algorithm is one of the most recent developed in 1999. It is comparison-based, using pointers instead of arrays and making no numerical assumptions on the edge codes. Its runtime is big O m times alpha mn. Here, the alpha is the inverse function of Alchemann's function, like the graph shows. Alchemann's function goes power tower grows rapidly, but its reverse function grows much more slow. And n is the number of the vertices, m is the number of edges. Bernard's algorithm utilizes a soft heap data structure. This achieves extract minimum and decrease key in O1 time. Soft heap uses associated numerical priority model, like a bridge between two extremes of always sorted and no guarantees on their order. Next. So this algorithm uses contraction tree design. The contraction tree is constructed according to pre-specified size constraints, and this tree is used to guide the MST building process. MST constructions itself occurs in separate phases. Here is a display of the pseudocode of building a contraction tree.
So we previously covered MST and RSTP, so now moving into modern solutions to the problem, we will identify why spanning trees have certain deficiencies for this problem. You get a loss of network links, specifically a tree representation of a mesh graph loses edges. Suboptimal pathing, because it's rooted at the root bridge, you do not have the best pathing necessarily from different leaves in the graph. Switches do not know the total network state. They're simply reacting to BPDUs that are flooded throughout the network. And you do not get multipath load balancing, which is basically if you have two equal cost paths from source to destination that can be balanced in level 3 networks. So getting into the modern solutions, everyone has basically abandoned STP technologies for adapting layer 3 technologies into layer 2 switch fabric environments. The modern solution we will cover is Trill. So to understand Trill, you need to understand ISIS. This is a routing protocol that creates a link state database, which is a totalizing representation of the network topology based off of shortest paths between all of the different nodes in the network. It logically segregates network segments into areas to reduce the total size of the cache on each router. It divides it into level 1 and level 2 systems to create a local area routing and inter-area routing. It forms adjacencies through hello packets, and once an adjacency is formed, all of the prefixes in the network are shared via link state advertisements. Shortest paths are calculated using Dijkstra's. Trill, which is a technology created by Radia Perlman, who was the woman who created the vanilla spanning tree protocol, uses a specialist technology called R-bridges to translate this layer 3 technology, ISIS, into a layer 2 topology. It does this via encapsulation. It adds a Trill header to each of the network frames, which has a TTL, a time to live, which indicates the total hop counts before it is discarded. Unicast traffic is added with these Trill headers on ingress from an R bridge to the egress R bridge, which holds the shortest path to the frame's destination, which is calculated by ISIS's Dijkstra. And multicast and broadcast traffic uses an MST rooted at a chosen R bridge and a reverse path forwarding check to prevent topology. So in conclusion, our exploration, MST algorithms are a suboptimal solution to this problem due to the fact that they inherently cause a loss of links and suboptimal routing. Almost all modern solutions, including SPB and Trill, work to translate layer 3 technologies into a layer 2 environment in order to make use of these redundant links. It's impossible to guarantee that the MST research we did will actually improve the overall runtime of multicast traffic in Trill because it's a proprietary protocol and we do not have access to the underlying algorithms. However, MST research could actually improve the total runtime and functionality of Trill.